here he's associated to ACTP, so we'll be visiting from time to time Trieste, and so we profit of this occasion to ask him a seminar about the semiclassical conformal blocks and record scaffolding. So please.
All right. Well, thanks. Thank you, Alessandro. Thank you for the kind invitation. I've been to Trieste many times actually, but somehow last time I visited CISA and got this talk to the mathematics department by invitation by David Guzzetti.
Yeah.
Who I understand is in Lisbon right now.
Yes, yes.
Right. Yeah. So.
We are the Portuguese. So
yeah.
I speak better.
No, although with a funny accent.
Yeah.
Yeah, I met him in Cambridge a few years, just before the pandemic, actually. Okay, so I'm going to talk about things I've been doing from the last 7 or 8 years. It's just a way to try to associate these ideas that, well, people in the audience are much better to talk about than me, to actual problems in quantum mechanics. So basically, the problems that we are going to work, the physics that we are going to work today is the physics of black hole scattering. So I'm going to try to explain to you why is it important to understand a little bit about this integrable structure. I'll be taking the CFT point of view. I understand that there are different ones, and why I consider this semi-classical conformal blocks to be the kind of special functions that you need for this enterprise. Some of the work I've been doing, use them a lot. I guess I understood fairly well how they are structured, and then I'll be talking about the structure later on, talking about the monodromy structure. I'll be jumping around the C=1 and semi-classical quite a bit. I don't know how well we're going to follow the language, but I understand this is a pretty informal seminar, so please ask me anything. If I know, I will be glad to answer. Right, so then I'll talk a little bit about the expansions at different points, and talk also about the point F5, so which sorts of comes about as a component case of the conformal blocks that people usually talk about, the CFTs. And I hope that I get enough time to talk about the applications, which are actually the physical purpose behind the enterprise. So anyway, there are a bunch of people that helped me along the way. I'm listing a few of them here. Julian Barragan Amado is in South Korea right now. And I understand he's applying for a postdoc in Lisbon with Giordano Cotti. So I guess that the circle will close finally. João Paulo Cavalcante he just graduated. He's beginning a postdoc at my university because he's too stubborn. Tiago unfortunately left for banking. I guess he's making more money than all of us combined. Fabio is a faculty at my home universities. Salman went back to Iran. He went to Brazil at the worst possible time, right before the pandemics, and he was stranded in the country for 2 years. Elisabetta, who's in Groningen, and Rodri and Darren, who are at Imperial College in London. There are a few more people that I should cite, but these are my co-authors. Anyway, let me try to motivate a little bit. I really apologize if I want to explain to you things that everybody already knows or heard to the death. But we'll talk a little bit about conformal field theories. So these are theories, field theories. So usually you talk about observables or local operators like this. which are invariant under a special class of symmetries. Usually, no, don't worry about that. It's okay. It's okay.
Okay,
it's okay.
You shadow point.
Yeah, I use the one I have.
Okay, very good. Okay, if you want.
So usually you hear a lot about this kind of invariance under the isometries of the space, like Poincaré group. But in order to study field theories close to the critical point or close to the renormalization group fixed points, it's important to include dilations as well. And most of the theories, they not only present invariance under isometries, dilations, and well, I guess inversions. They also have what is called the full conformal group, which also includes, apart from those, also include these special conformal transformations. And there is a whole industry of how to do that. It's beginning since the 70s. It's a bit underappreciated, in my view, but anyway, it's the tools that we have to talk about these field theories. Particularly interested in these field theories are operators which have a nice transformation law under these coordinate transformations. These are called primary operators. They are basically, if you think about x prime as the result of some dilation operator, you see that this basically has some definite scaling dimension. This delta that's parameterized by the delta. This symmetry, the full conformal symmetry, is enough for you to fix the structure of of 2 and 3 point functions for these operators. So if you have a special state here that's invariant in the conformal group, the conformal symmetry or the conformal transformation of this primary operator, the operator that respect that symmetry law, will be enough for you to fix the functional structure of these 2 point functions and 3 point functions. It's a major result. And this also can be interpreted in many ways. The way that we usually interpret is that this allows you to define a sort of inner product between operators in the conformal field theory, and this allows you to define a conformal structure constant for a type of algebra. That means that you can, in some cases, substitute the product of 2 operators with an X or with a third one. So this defines to you an algebra, and to try to use this algebra to compute a genetic endpoint function is called what is called the conformal bootstrap program. Anyway, in 2 dimensions, you not only have those finite dimensional group of transformation, you also have an infinite dimensional one, because in 2 dimensions, any analytic function generates a conformal transformation for you. So you have an infinite number of operators, and well, due to something that I'm not going to explain here, you can get the representation of the Virasoro algebra as the symmetry group of these transformations. So usually you only have this fixed part here, which can be thought of the Vit or diffeomorphisms of the circle algebra. But when you represent that into the space of states, you can usually you do have a center extension. It's parameterized by another complex. Well, treating that as a complex, so usually the people talk about real number C. And you can do more. You can construct a space of states. You can associate to any primary operator a primary state that I will use this to parameterize. And by working out how the algebra acts on these primary states, you can deduce that the primary state satisfies some conditions. So, for instance, this primary state is annihilated by all these Ln's for positive n. It's an eigenvalue of L0, and it's annihilated by all Ln with n positive. That's a dual state that represents, this is just a statement of the BPZ in the product again. So you have a dual structure here, and the dual structure induces some notion of some evolution in this operator, in the space of operator algebra, that, well, under which this These states are the analog, the adjoint to the states in this inner product. Anyway, and it's annihilated by all n, l, n with n positive. If you act on that with n, l, n negative, you're going to generate new states. These states are not primaries anymore, they don't satisfy these conditions. They are eigenvalues of L0 with eigenvectors of L0, eigenvalue delta plus n, and given here by this combination, and they are called descendants. So this is a way, and usually it's a procedural way to compute this space of states that all descendants on the state generated by some particular operator figure out. Well, what is that for? Well, you can use that explicitly to follow up the bootstrap program. In this case, to compute the 4-point functions. So you can use some the general conformal transformation to fix some of the dependence, and in the end of the day, you only have one position being linearly independent from the rest. That's I will call that T of conformal the harmonic ratio. It's just the fact that with the conformal transformation, you can map any 3 points to fixed points. So we usually fix them to be 0, 1, and infinity, and the fourth one will be mapped to a generic complex point in the complex plane T. So if you use this algebra that you define in the space of operators, you can decompose any of these two products into a combination, a particular combination here that I call psi, and this particular combination will include some primary operator and the descendants with some particular coefficients beta here that I'm writing. So I write L minus 1 VP, and if you remember from last slide, this L minus 1 VP is just the first descendant of the state that's generated by this. So you can compute these betas using conformal invariance. It's a very strenuous process. It's very complicated, but in the end of the day, you can write these 4-point functions as a decomposition in different, what we call intermediate channels. By that I mean that I only consider the OPE between these two and a particular vertex of a particular primary operator parameterized by P. P is any index. I'll tell a little bit more about that soon. And the extensions that I write here are functions of this T. There's an explicit T dependence on any term here. And this function is determined only by using Virasoro algebra. So they basically they only depend on the conformal the eigenvectors, like the eigenvalues of L0, which are usually called conformal dimensions, deltas, and the central charge. So these functions here that are specific from the Virasoro, they're specified from the Virasoro representation. They are, furthermore, in this case, I'm extracting this first part here. They are also analytic. This is also something you can get from here because this will give you a series in T. And of course, you're going to assume that the series converge. This should be T here, not T, not, sorry about that. And this f, this function f here, is something that I associate with the decomposition of the generic 4-point function, first of all. I'm missing a term of the conformal of this structure constant here. And they are determined from the conformal algebra, I told that already, and they are analytic when T is small enough. So these functions f, they are usually called conformal blocks. They are building blocks for 4 and higher point functions.
Can I write every conformal function like this? Or these are a special kind of
you mean this?
function? Yeah. I mean, can every conformal function can be written like that? Or no?
I'm not sure what you mean with conformal function.
I mean analytic, I'm sorry.
Mm-hmm. No, look, the thing is that we have this particular 4-point function here, right? This 4-point function, I'm defining that as a function of T. And you can work out the coefficients of this expansion of this function using the Virasoro algebra for any deltas here, for any values of delta. I don't know if that answers the question, but this is what I can do. Of course, I'm not assuming that this, well, I can have problems of this being not convergent function. But usually you have some structure in here that allows, that guarantees, at least if you're talking about the unitary CFT, guarantees that this function will converge for t is less than 1. So, okay, so what I mean by having a unitary CFT, I mean that first of all, there is a relation between the deltas and the c's. So I have to work in the. I cannot have a degenerate representation of Virasoro algebra. But if those conditions, the criteria are met, then I can write this. It's just that it's very complicated. It's not easy to compute these coefficients if you follow this. Anyway, so at this point, I hope that you didn't come here for black holes, because at this point you might be asking, what's the point, right? What I'm talking about. But some comments along the lines of your question. That I decided to decompose this 4-point function in a particular way, and this gives you an expression of this function f around t equals 0. If I decompose a different way, I can get, so for instance, if I do the operator product expression between this operator at t and the operator at 1, then this operator, the operator will converge in a radius, in a disk containing 1 and t now, not 0 and t. So that will give me an expression of an associated function at t equals 1. Or I can even do the one at t equals infinity. Remember, this is the Riemann sphere. It doesn't, t equals infinity is just another regular point. There are, in order to actually compute this, you have to work. So you can do the thing that I tell you, it's usually called the diagonalization of the Katz matrix, which is the matrix of inner products that you compute from these descendants. You can compute the f using that. It's very slow, but you can do that. Recently there are new methods. So one that's particularly interesting for all the connections, and I guess the people here are very experts on that, is using Nekrasov functions. Nekrasov functions, they are special type of special functions as well that show up in the instanton counting of n equals 2 superenigmas in 4 dimensions. It's something that has nothing to do with this, but through the AGT correspondence, that should be related to conformal blocks. So you have n equals 2, some matter multiplets mimicking the primary operators, and the instanton partition function of those should give you the conformal blocks of a 2-dimensional CFT. There's a mapping between the set of charges, the channel of the inner of the intermediate operator, and so on. There are other extra points about AGT which I'm going to touch soon. But the problem that we usually have in computing those is that they are very slow. I mean, from the computational point of view, they are very, very expensive. They are exponential usually. And the point that I have is that because of what I'm talking to, I'll be interested in computing them using some more or less efficient algorithms. There are some algorithms in the market. So, for instance, there is something that Sabalotchkov figured out about the pole structure of this conformal blocks. The guy is very smart, so he just trying to see which are the pole structure and what the pole structure should correspond to. So it's a bit like this theorems in complex analysis. Once you get the pole structure and the residues, you can recover the function. And that's actually a very fast algorithm to compute those. There are some other using because of the AGT connection, now you have this whole bunch of results on computing instantons in n equals 2 CMUs, for instance, equivariant localization. And there are another, I guess, integrable system inspired ways of computing those. There's a very nice application from these two guys here that allow you also to compute those more efficiently. Right.
What do you mean by AGT correspondence?
Well, I'm talking about CFT here. People in the room are experts in this part, mathematical part of it. So I'm talking about physics here in a way. I guess people from Conformal will take issue by me calling CFT physics. Anyway, they are not in the room. But here you have a whole, it's like a duality. You have a whole different terms for the same stuff that you usually have in conformal field theory. So, for instance, when you talk about superunions, you talk about flat connections, this ADHM construction, and all this stuff. And of course, there are no analog in CFT. One such relation are called the blow-up formulas. And the blow-up formulas is something that people know since the beginning of the 2000s in the Young cycle. It turns out that these have a correspondence in CFT, which is not something that you usually talk about in representation theory. Usually in representation theory, you set the Virasoro algebra, and you talk about a particular representation with a particular highest weight state. The AGT connection, or the blow-up formula, tells you something about what happens to it's a sort of Clebsch-Gordon term, but with the representation arising from two different values of C, for instance. Because they have some odd interpretation in AGT, which probably you should ask these two guys about. That will be allowed, they will be able to inform you much better. But that means that it's not something you think about when you're talking about CFT, but it's something that's natural to come about if you're talking about Young views. So in the end of the day, you can derive different formulas, like these formulas from blow-up, that in the CFT language, they involve representation theory of the Virasoro algebra at different values of C. And you can use those to sort of reconstruct the conformal blocks. In a way, it's similar to Zamolodchikov considerations of the conformal block when you see that as an analytic function of the central charge. Because you can always play the game of trying to find the poles, so for each values of central charge, the F will blow up, and try to compute the residues. But I don't think that anybody actually spell out the whole interpretation, right? At least what the blow-up formulas mean in CFT.
No, I mean there is an interpretation in terms of intertwining of representation.
Oh, right, okay.
So.
So it's basically what I said. Yeah. It's basically what I said. Okay. So yeah, the AGT not only tells you how to compute these things. I mean, Nekrasov functions are nice, but from this perspective they are not so helpful. But the problem is that they come from this whole different point that allows you to think about many structure that you couldn't find here by only thinking about CFT terms. Okay. Okay, but I talked about a lot of structures, so let me try to tell you why I'm interested in that particularly. Well, I talked to you a little bit about this matrix of inner products. We call the Katz matrix, or sometimes called Katz-Shapovalov. These are zeros that you find at the determinant of the Gran matrix of inner products of these descendant states. The zeros, of course, will arise when some states become degenerate, so they become zero norm. And they will become zero norm if the dimension, the eigenvalue of L0 for the highest weight states, falls into any of those points. So if you have any of those, here with m and n being integers greater than 1, I think, yeah. greater than, one or larger, right? And for these particular values of delta, so delta is the dependence on C here, and B is also parameterizing C. This states will induce, or the descendants will induce, at some point we'll have a zero norm vector. Well, I will give you a simple example. So if you have a particular value for delta to 1, which I did not write here, but it's minus 1/2 plus b squared over 3b squared over 4, then you can show using the Virasoro algebra and that notion of adjoint that I told you about, that this state here has no norm. So this chi here is a no norm vector. Now, having a no norm vector in quantum mechanics means two things. First, if you have a positive definite Hilbert space, being no norm means that the vector is 0. I'm using a slightly less drastic point of view, that I'm calling a vector 0 if it's orthogonal to any other vector. And that allows me to interpret this states in quantum mechanics, because if a vector is orthogonal to any other vectors, then the probability for the amplitude for me to find this state overlapping with any other state in your theory is 0. So this state should be coupled. Of course, this is not so simple, mathematically speaking, but this is what you expect physically. Right, so this way here, you write this as operators, so this is sort of masked, but there's a clever way to recast that as a word identity, so as some set of partial differential equations that correlation functions involving the operator associated to this node state should satisfy. So in this particular case, I'm writing one of them here. You have the second derivative with respect to the position of this node state, plus this combination of first derivatives with respect to the k, position of the odd operators. They should just annihilate annihilate is the wrong word, but anyway, this particular combination of primary states with the null state included in should be a solution of this partial differential equation. Usually this partial differential equation has lots of terms which are not determined from usual covariance. Remember that this term here involves only primary operators, so you know how this should transform on the conformal field, conformal transformations. So you have another set of first order partial differential equations that they satisfy anyway. And the second order is a bit more complicated. Well, it doesn't mean that this is completely useless. There are, I should probably talk about, there's one case where this is actually helpful, is the particular case where you have three states here, three vectors here, three operators here. In this case, you have a partial differential equation involving four primary operators, one of them being this generic. You also, so here you have a second order differential equation, and you also have another set of differential equations arising from the conformal symmetry of these states. So you have four variables, zk, and you also have four differential equations. One of them is second order, but no matter. This system can be reduced by to a first order differential equation that you can solve explicitly using hypergeometric functions. And you can use connection formula for these hypergeometric functions to determine, for instance, the value of the 3-point function of the conformal structure for these three operators that you have here. And this is a way to solve this bootstrap in two dimensions for Liouville. So, I mean, it's difficult to extract information, but sometimes you can do that. And the information that arises from that is interesting. In our case, it's a particularly It's derived from that somehow, but we are particularly interested in what I call the semi-classical limit. Sometimes it's called just the classical limit. It is a limit where you get the central charge to infinity. So the way I'm parameterizing the central charge, I didn't tell you about before, but I'm using this b to parameterize it, and I'm taking b to 0 using the usual way to do this. You can see that the central charge is basically invariant of the b going to 1 over b. So you could take b to infinity as well. Now the conformal dimensions. This is what usually is different between just purely classical limit and semi-classical limit. Is that the conformal dimensions also are going to blow up. So I'm also going to take them to infinity in this scaling limit here, and I'm going to do that with this intermediate dimension. So first of all, why this is called the classical limit? Well, if you write the action for Liouville field theory is just a way to parameterize the space of states here. You find that C square root, well, C over 6 just multiplies the action. So just do it with the definition. So B plays the role of square root of h bar in that case. And you can see here that when you do this sort of scaling limit, these dimensions become large, so in a sense the operators become heavy. And you can use classical solutions of Liouville to associate these deltas to conical defects in two-dimensional surfaces. That's actually where this program began. It's another point. It's another point that you have that these conformal blocks that I just defined to you, they exponentiate. So you can write them as the exponential of some other function here I'm calling w, and these w's are usually called semi-classical conformal blocks. If you use this analogy between classical mechanics arising from the system, then w would be just the effective action with the background that you have here.
I have a question. In this semiclassical limit, my algebra can become a Lie algebra, actually?
It is a Lie algebra. It's just an infinite dimensional one.
Okay.
It's just the Lie algebra will have an interesting
This
limit because it's a non-trivial limit because this is going to infinity, sure, but also you have to rescale this because you want to the L0 also to come infinity.
So can I interpret this exponentiation of the W function as, the set of this exponentiation, can I interpret it like the configuration space?
It is the action. It is the classical action of the system, in a sense. You're doing this. It's usually doing this backwards in field theory. So let me explain. If you begin with the field theory with the Lagrangian, if you do the expansion, if you do like perturbation theory, usually you hide h bar in there somehow. Like if you do QCD, the h bar is encoded into the G, into the QCD count. If you take h bar to 0, it means that the quantum fluctuations of your system will be suppressed. So in order to compute the effective action, for instance, it's something that you want to compute, you can stop at 3 level. And what is effective action at 3 level? It's just a classical action. Here we're doing sort of the opposite, everything in the opposite direction. You have some Hilbert space, which is supposed to be encoding all the states of your system, and you're working a particular limit where, first of all, these states, the Hilbert space is generated from fault construction from a Lagrangian, and second, the Lagrangian is given by this, the effective action, I should say. It's not true always, but it is true in this classical limit. Anyway, right, so the point for us will be to compute this, and it will become clear soon. If you have this limit now, this operator becomes, I told you that all these operators become heavy, but this operator does not. It's still light. So you can think of this as a perturbation in the background set by those, and then you immediately arrive to the point where this correlation function should factorize as this conformal block here, and this wave function associated that carries all the invisible pairs. Now, if you go back to the word identity that I wrote before, this partial differential equation, that means that the derivatives with respect to zk here, they only, the important bit only acts on w, because this is carries this 1 over v squared, 1 over h bar term. The derivatives of zk of this they do not carry b, so they basically vanish in the b equals 0 limit. So that means that this coefficients that you have here, that depends on the derivatives, they only become constants. So I'm calling this constants, this derivative of this w here, so it's the log derivative of f. And these constants, they then determine this function here that arises in this expression. Now you're going to have a second order differential equation. Here you're going to have some function with double poles and single poles, and this partial differential equation becomes an ordinary differential equation. Now furthermore, this ordinary differential equation is Fuchsian, is of the Fuchsian type. So you have at most polynomial blow up at each of the singular points. Now, to determine this coefficients, these constants here, is a particular problem in the theory of ordinary differential equations. It's actually the original form of the Riemann-Hilbert problem, which I guess many of you have already seen. The C here are particular, they only depend on the positions of these vertex operators and this conformal dimension, both of the internal one and this. Right. So now I'm going to, there are many ways to solve for this Riemann-Hilbert problem. I'm using a particular one that talks about the analytic structure. Now, right, so let's start from this ordinary differential equation. Usually, an ordinary differential equation, so now I replace this operator here with some function. Usually, ordinary differential equation with two derivatives here, we have two linearly independent solutions. You can think of a little bit of what those mean. And they arise from the strange fact that if you have a degenerate operator, every time you're going to multiply that with some generic primary operator, instead of having many results or many channels as a result, you only have two of them. You either have sum of this momenta, or you have this other, the difference of the momenta. So this is sort of the conformal families that arise. So you have two different conformal families. What you have here is basically analytic around the singular point, or around the coincident point between these two. And this factor here at the front only tells you what the differences between the two conformal dimensions of these operators are. So basically you have this structure that, well, we have some constants which you can compute, but I'm not interested in them. You have this part which is non-analytic near zk. So this exponent here may not be 0, or may not be an integer. And you have some other part here which is analytic. Here you have some other non-analytic bit with a different leading behavior than this. And you have this expression here which is analytic. So you can actually differentiate the two of them, the two solutions, by looking at this composed symmetry. So if you take Z to a monodromy around ZK, This part here we pick up some phase. I'm thinking of this as real for now, but soon I will generalize that. And you have another phase here. So you can differentiate these two families by looking at the monodromy properties around the point. This is again common to Fuchsian differential equations. Usually, when you write the Frobenius method, you have two solutions for initial exponent, and the two solutions also have different leading behaviors. Usually in physics, you only deal with one of them, you throw the other out, but here we'll be interested in both of them. So, try to explain in words what I just said. So, each Frobenius solution that you compute from Frobenius method in your mathematical physics course, of this word identity that I turned into ODE, they correspond to a different conformal family between the degenerate operator and the non-degenerate operator. Now, the Frobenius solution will allow for the calculation of the semi-classical conformal blocks, at least near the collision points. I'm going to explain to you right after this how to do that. The expansion of the conformal blocks at different points are related to what usually people call fusion rules. So in the way you decompose the 4-point function through the one type of OPE, you can decompose from a different type of PEs, and you can relate the two of them from these fusion rules. Fusion rules are not easy to compute, but for the genetic central charge, I don't know if I don't think that there are any way. Certainly there are many closed formulas, but I don't think there are any way to easily compute that. Now, we can do better using the ODE because this theory of differential equations, you have some special solutions that will be important for us that are called flow case solutions. That basically correspond to what happens if you take two of the primary operators and group them together. So if you consider the OPE between two primary operators with a particular weight. And then I'm going to show you how to use them to compute this fusion rules for semi-classical conformal blocks. So in principle, you can compute the semi-classical conformal blocks from this monodromy structure, but you need to know a little mathematics to know how this structure defines the conformal block globally. That means for any point, because this part here is hard to come by, the part about fusion rules. So if you do that, you can actually solve this Riemann-Hilbert problem. Okay, so let me try talk a little bit about the monodromy properties of this. So I told you that these expansions, they have this this structure that you have a leading term that's non-analytic, and then you have a trailing series that's very hard to compute, but in principle it's an analytic function. So that means that I have a solution of that particular ODE with a particular leading expansion around one of the collision points, and then some analytic structure. And I'm just using this term here as an illustration. If you have four primary operators and one degenerate one, you're going to have this kind of solutions for each one of these points. So you have two different solutions. I'm mapping them to plus or minus theta here, but you can have some extra term, it doesn't matter much. Only the difference will matter for the argument. You have two solutions at each of these points. But look, this is a solution of second-order differential equation. There are only two linearly independent solutions, so they must be related. How they are related? Well, I'm going to do something here in a sort of roundabout way to arrive at some conclusions that you have arrived to last year. Well, first of all, I'm going to consider this sort of solutions to the differential equation. They are not the Frobenius solutions that you usually talk about in the theory of partial differential equations. They are called flow case solutions. What are those? Well, I'm going to assume that I have a solution with this leading behavior that has not a analytic expansion, but a type of Lohan expansion. And the Lohan expansion, I will assume, will converge in an annulus containing both or two of these singular points. Well, if I'm lucky enough, I can find these A's, of course. For now, I'm just assuming that this is it, that this exists. Now, this function here will basically only work if you introduce an extra factor here. I'm calling this sigma. And this factor, sigma, will be related to the to this accessory parameter that I wrote in this term here. There will be a relation between these two. But if I introduce this factor, I can try and solve for the solution, and with some luck, I can have something that converges around here. Now, if this if the Lohan series converges, then it converges to an analytic function in an annulus, so you don't pick up any monodromy property from there, but you do pick up monodromy properties from these 2 points here. And you see that if I go around a circle containing both z and t, sorry, 0 and t, you're going to pick up a phase that's proportional to sigma. So sigma parameterizes this compound phase as you go around that. And this is called the compositive monodromies. And I did that with 0 and 1 here. 0, 2 is t, yeah. But you can, of course, make that between 0 and 1, t and 1, or any other combination. You basically have only 2, as you're going to find out, different such Fourier solutions. And they parameterize what I will call this, with the sigmas, I will call the composite monodromy parameter. Now, what is the monodromy here? What is this thing I'm talking about? Well, if you have a Frobenius solution like that, then if you go around, so if you pick some fixed point here, you go around one of the fixed points, say Z1, that means that I'm going around Z1 here. That means this part is analytic, so if I go around, it doesn't, nothing happens, but this part has this in principle, genetic exponent. So I'm going to pick up a phase here that's e to the I pi theta k. If I take the other one with the negative sign, I take another phase with e to the minus I theta k. So that means if I go around this loop here once, I'm taking these parallel solutions and multiply one of them by this and the other by that. So I can represent that using this nice matrix. This will be important because, as I told you, there will be some corresponding matrix here for Z2, Z3, Z4. And they all be of this kind up to conjugation. Because, why the conjugation? Because I told you that there are only 2 linearly independent solutions. So the 2 solutions that I construct here should be somehow related to the 2 solutions that I construct there and everywhere. So, in the end of the day, I have the monodromies around each of the single points being of this conjugacy class, and they all multiply in this manner to the identity matrix, because if I go around each of the single points, I'm doing analytic continuation around all of them, and the curve that I'm just drawing with my finger is contractible in this field. So, the analytic continuation does nothing at all. Now, you can work out the number of different parameters that you have here. It's a 2 by 2 matrix, and you have 4 of them. But you know there are traces, because you know it's in the conjugacy class, you know the determinants, so you have only 2 different parameters for each one of them. You have this constraint, and you have this remnant of the conjugacy invariance that I talked about. So in the end of the day, if you have 2 parameters, you can construct a explicit representation of these 4 matrices. So, sorry, you only need 2 of those parameters to characterize the monodromy matrices properties. Now, suitable choice is to choose the parameters to be this sigma that I introduced before, to be this composite monodromy, if I go around both of the loops, and the zeta parameter here, which is a very complicated function of this composite parameter, but it has a nice property. It is a conjugate variable to this sigma in a particular nice geometrical symplectic structure that you define, that's called the golden bracket on the space of monodromy properties. Now, if you are somehow able to construct these find these values of sigma and eta from the differential equation, then you can find an explicit representation of these variables here, and they are sort of canonically conjugate to each other in the classical mechanics sense. So, but the map between these two is a map between the parameters of the differential equation, which I'm parameterized by these thetas, correspond to the difference between the two indices, the two initial exponents, and the accessory parameters on the differential equation, which in this case is only one, and the position of the anamonic equation. So we still have two different variables here, keeping those fixed, the thetas fixed. So that means that if you find a map between this and this map should be symplectic in the classical mechanics sense. So it's a canonical transformation, really. Now, what is this canonical transformation? Well, it is something that's related to isomonodromic transformations, and I guess I just jumped the gun here a little bit. But let me tell you explicitly how to compute this. Well, I'm assuming for a small t that the c is just the derivative of this semiclassical conformal block. And because it's a symplectic homomorphism, it means that if I find some integration function here, I can once I recover this w from this c, I can integrate that and then differentiate that with respect to sigma to find the value for the canonically conjugated variable. So it means that I'm seeing this w, or w plus this integration variable, as a generating function for this symplectic transformation, this canonical transformation between these two. Right, and I told you that this sigma is related to c in a more or less well-defined manner. Well, what is that? I just plug the solution, this ansatz actually, to the differential equation and hope for the best. Well, it is lengthy, but you can do that. You can solve that using this three-term recursion relation. These coefficients A, B, C, and E that show up in this three-term recursion are functions of sigma, the accessory parameter, and the thetas, and you find some relation between them. It's in a continued fraction manner, and this continued fraction manner will tell you it's an implicit relation between sigma and c. So this, in a way,
this three term you get by inserting the Floquet
into the differential equation.
Into the differential equation.
You have to do a little fiddling, but basically it is.
Any of them. Here you chose one, but here you have all the exponents that appear, no? So how you get that all the exponents appear if you choose just a local solution around one?
Why? Right. It is a non-trivial fact that if you have, perhaps it's not so difficult to see, but if you just change in this particular parameterization here, if you change sigma by 2 minus sigma, you get the same c.
Mm-hmm. So
there are in principle there are two values of sigma that correspond to the same c. Basically. Is that your question? Perhaps.
No, I would say, I mean, you insert the Floquet expansion around, say, the point Z1.
NZT, yeah.
NZT, okay, in the differential equation, no?
That's right.
But that knows only about the two local exponents.
Yes.
So how the other local exponents appear in the?
Oh, because they are these local expansions.
Yeah.
Well, the exponents they are functions. They are parameterized in the differential equation.
So in the they appear in the potential of the differential.
Exactly.
Okay.
The only non-trivial bit that's not related to local exponent is the accessory parameter. Right. So if you can extract the expression very easily, although to be frank, I mean I'm really puzzled why we spend such a long time in mathematics trying to define functions from the expansions and not from this type of relation involved continued fractions that may be ignorant in literature. But this is in a way this is what defines this relation between this accessory parameter C and sigma for me.
Yeah, it's a way to.
But anyway, you can have actually an explicit series expansion by just imposing a form like this, and then using the formula that I just wrote to solve for the coefficient C here recursively. So you get the usual semi-classical expansion for the conformal block without any problems. Now you can integrate that, and then you're going to find W with respect to T. And then you can find this integrating function, that's only a function of sigma, by using isomonodromic methods. So this basically defines to you this function W of C here, and this F here, which is this T independent term is set. So you basically know this function W of T.
But this non-analytic term in T is.
Sorry?
The first term, C minus 1.
Uh-huh. Yeah, it's here. It's
okay, because you get the logarithmic term.
Yeah,
okay. Okay.
So.
Yes, that's all right. Yeah. No, they won't. Yeah. Yes. Okay.
So there is another way to look at this coming from isomonodromic deformations, and this relation between the I wrote beta here, but I should have written C. But the relation between the accessory parameter and the monodromy properties can also be defined through the Jimbo-Bueno tau function for this isomonodromic deformation. Well, I'm not going to talk too much about this. I can talk about if you want to, but the important bit for us, at least for this game, is that this expression defines the accessory parameter globally, not only as a series expansion of 1 equals 0, defines it everywhere. So if you could compute T, if you could compute the tau function for any value of T, you could use this expression to define the conformal, the accessory parameter. So you see that the same sort of thing shows up as W there. Here you have the log of tau function with some parameters related to the thetas that I had before and sigmas. They are the same in beta. And you have this auxiliary condition here. So the natural conjecture that you can pose at this time is that this gives you for eta being such that associated tau function is 0, this gives you the semi-classical conformal block. But I have no way to prove that. But since I know that...
Well, you can use the block equations, no?
Yes. In this way can do that, yeah.
That statement.
In this way can do that, but it's kind of hard to invert this, right? And substitute that. Anyway, the important bit still remains that this defines this accessory parameter not only as a series, but globally in the complex space. Global for any value of T. incidentally, the same tau function, this tau function, can be computed anywhere in the complex plane, because there is a very nice formula that writes the tau function as this kind of Fourier series involving not semi-classical conformal blocks, strangely enough, but C equals 1 conformal block, sort of the deep quantum part. Instead of being B equals 0, it's B equal I. And this expression is the now famous KF formula, which was baptized here, as I understand. But it was found about 10 years ago, no, 11 years ago, by these three guys that were working here at the time. And there was lots of work actually on this, and the important bit for us is that they have ways to compute this conformal blocks, in this case only using C equals 1 fusion rules for any value of t. In a way, this the point is that you have a special function, so like a Bessel function. What it means to use Bessel function to solve problems in physics? Well, you do, if you don't consider Bessel function to be elementary function, you say that if you write something like in terms of Bessel function, you're not really solving it. You're just using Bessel function as some shortcut for some function that you don't really understand how it works. What saves you is the fact that Bessel function has lots of structure. There are some points that you're going to be able to answer, like for instance, how to compute the derivative of Bessel function in terms of Bessel function, what is the asymptotics, and so on. But there are some points which are not going to be able to answer because it's a different function. Now, where are the zeros of Bessel function? We have some asymptotics, but usually you have to have some table because you can compute that numerically. It is the same thing with the tau function. That's what these people actually have argued. Is that expansion, the tau function is a function that's defined on the whole of the complex plane. Well, you have branch cuts between 0, 1, and infinity. But you have asymptotics of the tau function at 0, at 1, and at infinity, and you know how to relate them. You have connection formulas between those. So, in a sense, this is the best you can hope for a special function. You have some ladder, you have this Hirota equations that allow you to compute tau functions with different arguments and so on. And there's some extra structure that saves you. But in the end, it's just another kind of special functions like the special functions you study about in electromagnetism. You can do some stuff, you cannot do everything you can by, for instance, with polynomial functions. Well, even polynomial functions, sometimes it's harder. You cannot find zeros for if the degree is high enough. So the point that we want to make here is that you can make this connection between the accessory parameter you compute using the semi-classical conformal blocks and this tau function to define these conformal blocks globally in the complex plane, just like any special function. Well, I told you that there is a relation between the tau functions at different singular points from brain relations. And that allows you actually to compute this function that I told you that I was going to present you, but here it is. It's just some strings of Euler gamma functions. And there is an important bit here is that it should be sigma, sorry about that. That the eta, the associated function that you compute from this derivative of tau function, automatically satisfies this condition. So it's actually it's very efficient, computationally cost-effective way to find zeros of tau function. I don't know if you find all of them. It would be nice if you have some results there. And the expansions can be worked out if you just like the expansions that you have here. So like this, the first line here, the expansions around t equals 1 and t equals infinity can be worked out by using this relation between the monodromy matrices, by using that allows for a relation between this monodromy properties, eta and sigma. So you're going to define 3 different single points, 0, 1, and infinity, and you're going to have different types of sigma parameter. So for instance, t equals 1, the natural composite parameter will be given by this particular trace, and an associate canonically conjugated in classical mechanics sense variable eta. This covers all patches in the complex plane, and this allows me to tell that these functions, they are not only related by some sort of Legendre transformation, they are really the same function. So it's sort of having different maps or in an atlas, and you'll be able to compute the function, and they give the same value at each one of them. So in particular, for instance, if you have the expansion around t equals 0 and the expansion around t equals 1, there is some overlap region in the complex T plane that you can use to compute these functions. And you can check that both of them give the same results. Right, just very, I'm already over time, so I'm going through this. It works the same way for irregular conformal blocks. Irregular conformal blocks are just some scaling limits of these conformal blocks that I told you about. You take some dimensions to infinity, whereas you take this t parameter to 0, just like a confluent limit. You also have this different expansions for conformal block that you can also use these Floquet solutions for the associated mode identity. You can do something different now. You can do a sort of Floquet solution, but for infinity. So you parameterize these WKB periods using confluent hypergeometric functions. And you find the same sort of three-term recursion relation that allows you to compute the irregular conformal block now, the expansion at infinity. Yeah, here you have this eta parameter that's ni parameter, sorry, that's related, it's oops, anyway, this parameter here that's related to the parameterization of the monodromy matrices at infinity, and you have some associated conjugate variable, but you also recover this irregular conformal block. It's actually a very efficient way to compute those in this semi-classical limit at least. And I use that, this is the end, to study black hole physics. Well, how am I able to use this to study black hole physics? Because if you do perturbation of black hole, usually this means, the black holes people take pictures of, these Kerr black holes. If you work out the Einstein's equations, the linearized Einstein's equations, you end up with with a separable partial differential equation that you can write as these two ordinary differential equations through the usual separation of variables technique. Now, these equations, oddly enough, they are not Fuchsian, but they are this confluent Hoyne limit, the confluent limit of Fuchsian equations, for what I call confluent Hoyne equation. And then, by bringing those to this form, I can read up the parameters, like this monodromy parameters, theta, and the accessory parameter Ct. And then I can use this machinery that I just described to you to compute the monodromy parameters. Now, why is that interesting? Well, the monodromy parameters allows you to compute things like, allows you to compute parts of the connection between the solutions at different points. Well, I would be released in not mentioning that this problem has actually been solved by people in this room using semi-classical conformal blocks. There's this nice formula that allows you to compute the connection between two different solutions, the ratio of two different solutions at two single points involving this semi-classical conformal blocks. And this has been done by these people at Kiev, the Trieste. So I'm not going to use this right now, but this is just to remind you that the ability to compute this semi-classical conformal block efficiently in the whole complex plane has become even more important now. Because not only are you able to solve the problem that I'm going to be able to solve, but you'll also be able to solve this connection problem as well, if you just be able to compute this W in the whole complex plane. So I'm just going to show you the results because this is all I have time for. You have the angular equation, this equation for S here. I'm just write that in terms of U. And this equation asks you for a solution that's well behaved both in the North Pole and the South Pole. So that gives you a condition to the monodromy properties, the monodromy sigma here. It just has to be this sum of these two up to a even integer. So if you can crank up the machine, and now to find the accessory parameter in terms of sigma, and sigma given by this, you can find the eigenvalue, which is usually called the spherical eigenvalue. And you can recover the expansion. And you can do this to higher order, and it doesn't really matter. But this method has been known actually for these people for like 40 years. It's nothing really new. The only thing that we sort of understood is how to understand this variable sigma here. You can do that for large frequencies as well. That's the new thing, because you can compute this W everywhere. So you can compute the eigenvalue as a large expansion in the conformal modules. This is proportional to the frequency. Mm-hmm. Strangely enough, this seems to be analytic in 1 over W. Well, there's this term here, there's a first order term, but the rest of it seems to be analytic. Which is quite surprising because the plane of F5 has a very complicated structure at the heat. The radial equation also works in the same way, because the singular points of the differential equation, they coincide with the positions, the radial positions of the horizons. So, for instance, the Frobenius solution that you write around here are purely ingoing at the horizon, purely outgoing. The Frobenius, not Frobenius, but the expressions, the Stokes solutions that you write here are purely ingoing and purely outgoing for infinity. They usually call the Hughes solutions. Anyway, and you can read up the monodromy parameters. There's a nice interpretation of monodromy parameters I can tell you later on. I just want to jump to results. You have some condition now that's a bit more complicated between the monodromy parameters, but you can use the conformal blocks to compute them. So this is something you can teach a computer how to do. You don't need to think. It works. There are two lines here, one in blue and one in red. They are superposed. You cannot see both of them. But this is this is just the comparison between the method that I just described to you and the usual method people use to work these things out. This papers where we present the results. The difference is actually very small, just 10th decimal place up to numerical precision, really. You see that the mismatch becomes larger here, so there's some structure here that you cannot see through the usual method. But our method seems to be working fine. So the extremal limit also can be studied. It gives you tau of the plane of F3. Mm-hmm. But yes. You have this doubly confluent Horn equation, which you would associate irregular conformal block to it. From the physical point of view, these modes are very interesting because in the extremal, limit of the black hole, so when the black hole is rotating very fast with the speed of light, basically, the modes that rotate along with the black holes, they are undamped. They become long-lived. The time of decay goes off to infinity. And these are usually called undamped, zero-damped mode or undamped modes. And we found an explicit analytic expression for that by just expanding the tau function. It's not really. So I'm just using this for illustration. These are the L equals M spherical harmonics that should correspond to these modes. Well, you get some analytic expansion of the frequencies. The real part goes to M over 2, and the imaginary part goes like this, and depends on the angle eigenvalue. Right. You can do the large frequency expansion, and just for you to get a hint of what I mean, I compute these frequencies using the small t expression of the conformal block, and I compute this using the large t. And you see that they match up to precision, up to machine precision. That means that I am able to compute and verify that the functions they give the same results in the overlapping region as they should. It's a nice plot here showing that the zeros of the tau function correspond to the solution of the problem, and you see that the zeros is isolated as they are supposed to. You try to submit that picture to the guy that has this calendar about complex functions. I'm going to put nice colors in there. And you can also study some very odd things that happen. For instance, you have this co-rotating limit for the black hole, so it means that in the extremal limit, all the eigenmodes for L equals m, and here you have overtones, so this is like the fundamental level, the first excited and so on. But all of them, they go to zero imaginary part in the extremal limit, except n equals 6. And this is the sort of thing I mean, right? I mean, is there an explanation for this? Probably not. It probably is just some fluke of the numerics, but it's like the zero of the Bessel function. You can compute that, but you cannot explain what that it is what it is. Anyway, finish up. So I hope I show you that I talked about a particular example, but of course everybody in the room has a different use for Fuchsian type of differential equations. The global properties are useful not only for CFT but in many other applications. In particular, I told you about how to compute quasi-normal modes of black holes efficiently using them. And there are some nice things that you take from this. For instance, I didn't tell you about, but the deltas that I have there, the thetas that I have there for the radial equation, they correspond to unitary CFTs. Even though Z, I'm taking R to be a generic complex number, but they correspond to unitary CFTs if the frequency is real. So I'm not sure if I should take that seriously, but it is what it is. And this is hopefully a very procedural way to work out the Riemann-Hilbert map, the map between the parameters in the differential equation, parameters in the Fuchsian system, two parameters of monodromy for genetic equations. So any problem, in principle, any problem involving scattering about states can be solved using this way. So there's some other things about resurgence that I don't have time to tell you, but anyway, thank you very much. I hope I didn't try your patience so much.